On October 20th, 2020, a spacecraft the size of a large van approached a mountain-sized rock tumbling through space 200 million miles from Earth. Its mission: touch the surface for exactly 6 seconds, steal a handful of dirt, and get out before a boulder the size of a 2-story building could destroy it. There was no way to steer it by hand, no way to abort in real time. By the time anyone on Earth knew what had happened, it would already be over. This is the story of OSIRIS-REx and the 6 seconds that decided whether it all worked. Let's start with why this asteroid mattered enough to risk a billion-dollar spacecraft on it in the first place. Its name is Bennu. It's what astronomers call a near-Earth object, an ancient chunk of rock and rubble left over from the early formation of the solar system over 4.5 billion years ago. Unlike planets, which have been geologically reshaped again and again by heat, volcanism, and erosion, asteroids like Bennu are essentially frozen in time. Scientists believe studying Bennu's material could offer a direct window into the raw ingredients that built the solar system, and possibly even the ingredients that helped seed life on Earth itself. There was another reason NASA cared about Bennu, one a little closer to home. Bennu has a small but real chance of colliding with Earth in the next couple of centuries. Understanding exactly what it's made of, its density, its structure, how it would break apart or deflect, is directly useful information if humanity ever needs to nudge an asteroid like this off a collision course. So NASA didn't just want to look at Bennu from orbit. They wanted a physical piece of it, brought all the way back to Earth so scientists could study it in laboratories for decades to come. The mission was called OSIRIS-REx, and it had been traveling through space since September 2016. By the time it arrived at Bennu at the end of 2018, mission scientists were expecting something fairly simple to work with. Earlier telescope images had suggested Bennu's surface was relatively smooth, maybe covered in fine sandy material, the kind of surface that would make a sample collection maneuver almost routine. They were wrong. When OSIRIS-REx got close enough to actually see the surface in detail, the images that came back stunned the team. Bennu wasn't a smooth little sandbox floating in space. It was covered edge to edge in massive boulders, some of them the size of buildings. The spacecraft's own science team ended up nicknaming one particularly enormous boulder near a candidate landing site Mount Doom, a nod to the fictional volcano from The Lord of the Rings, because it loomed directly over one of the safest-looking patches of ground nearby. Suddenly, a mission that was supposed to involve landing, or more precisely, briefly touching down in an open, forgiving area became something closer to threading a needle. The team spent nearly 2 years mapping every square meter of Bennu's surface in extraordinary detail, hunting for a patch of open ground large enough and clear enough of hazards to safely bring the spacecraft down to. They eventually settled on a small crater they named Nightingale, a site barely 16 meters across, hemmed in on multiple sides by boulders that could destroy the spacecraft on contact if it drifted even slightly off course. To put that in perspective, OSIRIS-REx is roughly the size of a large van. Its target was a patch of ground about the size of a few parking spaces, and it had to hit that target while approaching an object whose gravity is so weak the spacecraft would barely notice it was even there. Every tiny thruster burn had to be calculated with extreme precision because there was almost nothing pulling the spacecraft naturally toward the surface to help. And there was another problem the mission engineers couldn't fully solve in advance. They didn't actually know what Bennu's surface material would feel like on contact. Would it be firm, like packed soil, or loose, like a pit of gravel? The answer would matter enormously, and nobody would know for certain until the moment of contact itself. Now here's the part where the distance really becomes the enemy. Bennu was so far from Earth that a radio signal took over 18 minutes to travel one way between the spacecraft and mission control. That means, unlike a landing on the Moon or even Mars, there was absolutely no possibility of real-time guidance, correction, or rescue. Whatever OSIRIS-REx's onboard computer decided to do in the final moments of its approach, it had to decide entirely on its own. Engineers on Earth could only watch it happen after the fact, and even then only through delayed telemetry data, not live video. On the day of the maneuver, officially called a touch and go, or TAG, the sequence began hours in advance. OSIRIS-REx fired its thrusters to leave its safe orbit, roughly 770 meters above Bennu's surface, and began a slow 4-hour descent toward the asteroid. As it fell, it extended its sampling arm, an 11-foot mechanical limb called TAGSAM, the touch-and-go sample acquisition mechanism, piece by piece, like unfolding a shoulder, then an elbow, then a wrist, until it was locked into its final sampling position. At an altitude of about 125 meters, the spacecraft performed its first precision maneuver called the checkpoint burn, adjusting its speed and trajectory to descend more steeply toward the target crater. About 11 minutes later, at just 54 meters above the surface, it performed a second burn called match point, slowing itself further and synchronizing its motion with Bennu's own rotation so that touchdown would happen smoothly rather than as a violent collision. Then came the most nerve-wracking stretch of the entire mission. An 11-minute coast, gliding silently past the looming shadow of Mount Doom toward the narrow clearing at Nightingale. No further engine burns, no more corrections, just momentum, physics, and months of careful planning, carrying the spacecraft toward a target roughly the size of a few parking spots next to a boulder that could end the mission instantly if the spacecraft drifted even a few meters off course. And then, contact. The sampling head touched Bennu's surface. Instantly, it fired a burst of pressurized nitrogen gas directly into the ground, not to push the spacecraft away, but to blast the surface material upward, agitating dust and pebbles so they could be funneled into the collection chamber, almost like using a leaf blower to kick debris into a vacuum. The entire contact lasted only about 6 seconds. Then the spacecraft fired its thrusters and pulled itself back away from the surface, retreating from Bennu as quickly as it had approached. On Earth, the mission team received confirmation of contact at 6:08 in the evening, Eastern Time. Not live footage, but a simple radio signal arriving minutes after the fact, confirming that touchdown had occurred roughly as planned. What they didn't know yet was just how strange that 6-second contact had actually been. When images finally came back days later, scientists were stunned. Bennu's surface hadn't behaved like packed soil at all. It behaved
almost like a pit of loose plastic balls. The spacecraft's sampling head had sunk far deeper into the material than anyone expected, essentially punching a fresh crater into the asteroid on contact. The mission's lead scientist, describing the images afterward, said it looked as though the surface had simply shattered and given way beneath the spacecraft's touch. That turned out to be extraordinarily good news, and then almost immediately a new problem. The sample chamber had collected far more material than engineers had planned for, so much material, in fact,
that some of it began drifting back out through the collection head's flap, slowly leaking particles of Bennu back into space. Rather than risk losing part of the sample they'd worked years to obtain, the mission team made the call to skip planned follow-up measurements and rush to stow the sample safely inside its return capsule days ahead of schedule before any more of it could escape. In the end, OSIRIS-REx brought home more than 60 grams of material from Bennu's surface, significantly more than the mission's original minimum requirement. The sample capsule separated from the spacecraft and parachuted down into the Utah desert in September 2023, nearly 3 years after that 6-second touch in deep space, delivering scientists one of the largest and most pristine samples of an asteroid ever collected. It's easy, watching the footage now, to see it as simple. A spacecraft flew out, touched a rock, and flew home. But every second of that touch was built on years of mapping an unexpectedly hostile, boulder-strewn surface, threading a target the size of a parking lot next to a landmark literally named after a volcano meant to destroy things, with no ability to correct a single mistake in real time from over 200 million miles away. 6 seconds of contact, years of preparation, a margin for error smaller than most people realize, and it worked.